Okay, so this title, of course, is a bit complicated. All possible couplings approach, it's simply, the name I gave to a particular approach that I'm going to describe. And it is related to the theoretic probabilistic notion of a coupling, and I will mention that a bit later. But the more significant two words, perhaps at the moment, are context and determinism, and they are significant because neither of the two words I actually understand or going to explain what they mean. I'm going to propose a formal mathematical way of circumventing the necessity of defining these terms and just placing them into a formal structure that allows us to discuss things on a very high level of generality, irrespective of how these context and determinism will be defined in any specific area of research. So first of all, I would like to acknowledge that this particular presentation is based on a joint paper, which is currently, after having been revised, is being under review. And it is available in this form, and I also sent it yesterday to Janet Phelps to attach to the conference website. So whoever is interested in more details, of course, is welcome to look at it. And then perhaps email to me with any kind of suggestions or comments or whatever. I would welcome it very much. And that paper is written together with Yana Kujala, my very talented collaborator in many papers. He is at the University of Jyväskylä in Finland. And the story begins with this type of diagrams. I call them arrow diagrams or diagrams of selective influence, whichever term one would fancy more. Alpha, beta, gamma, delta here are inputs. And A, B, C in this particular example, obviously it is just an arbitrary example, are outputs. And A, B, C outputs are random variables, whereas alpha, beta, gamma, delta are deterministic inputs. It doesn't mean that actually in the nature they have to be deterministic. It only means that my way of considering this system of inputs and outputs is that I am observing the values of A, B, C conditioned upon specific values of alpha, beta, gamma, and delta. So even if alpha, beta, gamma, and delta themselves are realizations of random variables, I ignore it, and I'm conditioning the joint distribution of A, B, C upon the combination of values of the inputs. So from that point of view, the distinction is strict between inputs and outputs. It is not like in let's say Bayes field diagram or something where you draw arrows between random variables. And the question here, which interested me, started to interest me a long time ago, was what does it mean to say that alpha selectively influence, well, in this particular case, what does it mean to say that A is selectively influenced by alpha and beta and by delta, but not by gamma. And B, the output B, is selectively influenced only by beta. C is influenced by alpha, by gamma, by delta, but not by beta. So how would you define this selectiveness in the influences exerted by the inputs upon outputs if for any combination of alpha, beta, gamma, and delta, which we refer to as a treatment or allowable treatment, the joint distribution of ABC is observable and ABC are not independent. If they are independent, the situation is relatively trivial and the definition is straightforward. If they are not independent for any treatment, or at least for one of the treatments, better to say, then the answer is not trivial. And there were several attempts to give this answer. Yes?
Are A, B, and C deterministic, mutually exclusive consequences?
A, B, C are random variables jointly distributed for every combination of values of alpha, beta, gamma, and delta. And you observe, so in other words, you're observing them together, A, B, and C.
Okay, so
right?
If I change gamma,
yes,
that causes a change in the random variable called C?
Right. Well, if you change any value of any of the inputs,
I'm taking the easy case.
well, okay, but you are already referring to selectiveness, which I have yet to define. So what you observe is that whenever you change the value of one of the inputs, the joint distribution of ABC changes.
So A, B, and C are each measures over some space.
ABC are jointly distributed. For any given input, they are jointly distributed. So it means that they are functions of one and the same random variable or defined on one and the same sample space.
Okay, so there's some sample space beneath A, B, and C.
Well,
You don't
yes.
care about it.
Well,
It doesn't matter.
actually, it matters a lot, but let me just be very, very cautious here because we are going to construct it step by step. A, B, C are jointly distributed for a particular input, for a particular combination of values of the inputs, for a particular treatment. If you change the treatment, so change the value at least of one of them, you are creating a mutually exclusive condition under which you are now observing ABC. Now, ABC, for two different treatments, ABC are stochastically unrelated. They are not distributed on the same sample space. But for any given treatment, A, B, and C are jointly distributed random variables. Right?
Would we say that A, B, and C are, that alpha, beta, gamma, delta are indices for A, B, and C?
Well, you can say that. In fact, alpha, beta, gamma, and delta, you can consider them indices for the sample spaces upon which A, B, C are distributed. Right? So if you have two values of alpha, two values of beta, two of gamma, and two of delta, and all of the crossable, you have 16 possible treatments. So strictly speaking, you have 16 stochastically unrelated sample spaces on each of which you have this triple of random variables jointly distributed.
Triple of mappings on some D,
Yeah.
on R1 or something like
Oh,
that.
well, that
anything.
you are kind of, anticipating what I'm going to talk about, right? So when you have unrelated unrelated sample spaces, you can then attempt to put them all together, and this is what coupling is about, right? And I'm going to talk about it. So this is the problem that was posed in psychology. In fact, it was posed by Saul Sternberg in 1969 in the context of discussing mental architectures. When you have hypothetical processes going on in your brain and you have experimental manipulations, these alpha, beta, gamma, delta, and before you can decide whether these two hypothetical processes are parallel or serial or whatever, you have to decide that particular manipulation selectively influences only this particular process, some other manipulations selectively influences this other process, and then you can try to reconstruct their architecture, how they are connected, right? So this was how Sternberg posed this problem. Without getting into history of that, the next major contribution was by Jim Townsend of Indiana University, who proposed actually for the first time to talk about this situation when ABC are not independent. But his solution is not the one that I'm using. The solution that I'm using, by solution I mean the type of definition that I'm going to use for selective influences, is the one that I proposed in 2003 and then developed, for 10 years now, and with significant contribution from Jana Kujala, whom I mentioned previously. So I have a general mathematical theory that defines what it means to have selective influences when you have an arbitrary set of inputs, arbitrary set of outputs, and the outputs can be of any degree of complexity, and the same is true about inputs. So it's completely general. And I have a set of tests confined to specific types of distributions of ABC that allow you to determine whether selective influence pattern that you postulated in the beginning, whether it holds or doesn't hold in view of what you can observe, right? These tests are usually necessary conditions. Under some circumstances, they are necessary and sufficient conditions or criteria. Now, there is a second problem that comes kind of in parallel with this one, but it has been ignored for a long time, including by myself. Usually in psychology, we're interested in whether the pattern of selective influences holds or doesn't hold. If it doesn't hold, we simply declare it doesn't hold. And that's the end of the story. But in fact, it's the beginning of another story. When it doesn't hold, in what way, to what degree, in by what type and by what quantity the situation deviates from the pattern of selective influences that you postulated in the beginning. So in some cases you can postulate selective influences kind of normatively and say, normatively speaking, it should be like this. But in fact, I observed that this is not the case. Now, is the deviation that I observe, is it a slight deviation from this pattern? Is it a gross deviation? It's especially interesting because, as I'm going to mention in a minute, this relatively modest problem in psychology turns out to be formally completely equivalent to a problem that has significantly more general kind of resonance, general visibility, namely the problem of existence or non-existence of a classical physical explanation for the quantum entanglement phenomenon. And in order to explain that, let me simplify the situation to this one. And I'm only going to talk about this one situation now when I have two inputs, two outputs. Alpha normatively selectively influences A, beta normatively selectively influences B. Moreover, even this is too complex for now, I'm going to assume that both alpha and beta are binary inputs, so they only have two possible values each, and that they are completely crossable. So the set of treatments is just the Cartesian product of these two element sets, right? So we have four treatments. For each of the four treatments, we observe the joint distribution of AB. Now, in order to make it even simpler, I will now assume that A and B themselves are binary random variables. So it's just a +1, -1, right? And finally, in order to make it super simple, I will assume that the probability of each of the outcomes for each of the random variables separately taken is 1/2. So they are equiprobable outcomes. So the only thing that actually is not known in this situation a priori is the joint probability of A and B being +1 and +1, or +1, -1, or -1, -1. So the joint distributions are not known, but the marginal distributions are known. They're fixed, and that is the simplest situation. Now, this, by the way, well, it is a very simple situation, but it is a very common situation too, both in psychology, when we discuss factors influencing dependent variables, and as it turns out, in physics, if we are confining our attention to so-called spin 1/2 particles entangled in the simplest possible entanglement paradigm, the one that Bohm invented after the classical paper of Einstein, Podolsky, and Rosen. So this is how the results of such an experiment, and by the result I do not mean statistical results, but let's say that you know the exact distribution, so statistical questions all aside. You know the precise distributions. So, and you know that if alpha is at the first level and beta is at the first level, then the probability of A being +1 and B being +1 is P11. This is what you know. And then because they have to add to 1/2, this probability is 1/2 minus P11. These have to add to 1/2, so it is also determined. And then this thing has to be equal to this thing. So essentially, the simplicity of this paradigm is that it is determined by four numbers, P11, P12, P22, P21, and this is the entire vector of observable outcomes that I'm going to base my discussion upon, right? Again, it is only an example I'm working out. The general theory is worked out in complete generality for absolutely arbitrary sets of inputs and outputs. But here it is something that we can handle computationally quite easily. Okay, so this is clear, right? And I'm focusing on these numbers, on these probabilities, and they refer to the probability of +1, +1. Now, just to give you examples, this is the example from my own lab. This is an experiment that we were conducting by matching one flower shape to another flower shape. So the one on the left is fixed, and the one on the right can be manipulated by manipulating these amplitudes, x, ij, y, ij. So this theta is fixed, so there are, in polar coordinates, if you imagine it's a circle, in polar coordinates it's described by this formula, and this is described by this formula. Alpha and beta here are fixed, but they can be fixed at 4 different combinations of alpha and beta. So these are my inputs, and this would create 4 different shapes that can be presented. And here you are starting with some shape, and by adjusting these 2 amplitudes of the Fourier harmonics, you are trying to match this shape to this shape. So you can do something like this and something like that. And of course, when you stop and say, well, there is a match, x and y are random variables. So if you do it 100 times, you will get with different pairs of numbers. They are jointly distributed, right? And these joint distributions you can evaluate, right? Now, it is far from being a binary random variable, but what you can do in order to conform the pattern of the results to this simplest case that I'm considering is this. For every alpha and beta, you can create 2 random variables depending, according as x or y being greater or below, greater than or below the individual median of the distribution, right? So there is a distribution of x's, and 1/2 of these things is above median and 1/2 below the median. And so you simply look at whether it's above or below for one harmonic, and the same for above or below for the other harmonic, and then you look at the joint distribution, right? You get exactly the result that we have already discussed. So the result of this experiment after this discretization can be described in this way. The equality of the marginal distribution, marginal probabilities to 1/2 is simply ensured by the choice of the median. Right? We're looking at the median. If I choose some other quartile, I would have fixed the marginal probability some other values. But I'm interested in 1/2, 1/2. Right? So, here I can ask this question again. This is the amplitude of the first Fourier harmonic. This is of the other Fourier harmonic on the input, on the left. And these are these discretized amplitudes on the right of in the picture that I've matched to the picture on the left. And I'm interested in whether there is a selective correspondence, whether this amplitude selectively depends on this amplitude, and this amplitude selectively depends on this one, or not. So we may find that it is the case, or we may find that it is not the case. And when it is not the case, we are going to ask the question by how much and in what way it is not the case, right? So the violation of selective influence can be of different kinds and to different degrees, and I'm going to propose classification and quantifications of these violations. Now, a significantly more famous example, this one. So in a singlet state, 2 electrons, let's say, running away from each other. This is Alice's particle, this is Bob's particle. And you have detectors set at one of 2 possible orientations or directions in space, this one or this one. And so Bob can, for example, choose this direction. Alice simultaneously, from the point of view of some observer, can choose this direction, and then they will observe whether the spin is up or down. Right? Its spin is here shown by this rotation thing, but so imagine that this is up and counterclockwise is down, let's say, right? The thing that's if you have two directions possible for Bob's detector and two directions possible for Alice's detector, then we have two binary inputs, right? The outputs are also binary because for electrons and spin 1/2 particles, the spin can have only one of two possible values, +1, -1, up or down. And and we can choose the state of the, this entangled system in such a way, and the plane in which we are choosing this direction in such a way that the marginal probabilities of spin being up or down for each of the particles separately taken is 1/2, right, which is the most standard situation for entanglement, right? So again, it turns out that we are only interested in these probabilities that A is up and B is up for every of the four combinations of the spatial orientations, and the quantum theory gives us this formula, so we actually know what this probability is, right? And in this particular case, if we plug in these probabilities into the test, I'm kind of anticipating a bit what I'm going to say, but let me mention it right away that there is a particular test for selective influences, and in this particular case, with these probabilities given to us by quantum theory, this test will be violated. So we know that selective influence is not present in this case. Right? So let me talk about it in detail. So again, I'm interested in whether the result of the measurement by Alice only depends on the Alice's detector setting and not on Bob's, right? And the result of Bob's measurement only depends on the Bob's choice of the spatial orientation and not on Alice's, right? And in this particular case, in addition to proposing it normatively with the possibility of violation, physics actually tells us it absolutely has to be like this, because if there is an observer from whose point of view Alice and Bob do it simultaneously, then they are separated by so-called space-light interval, and light cannot travel from Bob to Alice or from Alice to Bob, so there is no way the dependence can be established in physical terms, right? Nevertheless, the selectiveness is violated, and it creates the necessity of talking about different types of determinism. So in fact, what physics proposes to us is that since it is violated, and since we do not want to reject special relativity theory, we want to invent a new type of determinism. We say that there is a quantum determinism, and it is more relaxed than classical determinism. And within quantum determinism, what we observe is possible, but not within the classical determinism, which corresponds to this diagram of selective influences. So let me again take it step by step. This is probably a natural definition. You can derive this definition from certain desiderata, certain things that you want a good definition of selective influences to satisfy. You can simply take it and kind of appreciate that it is a very natural definition. You have A and B observed for every ij. Ij, remember that these are indices corresponding to the values of your inputs, right? So 1, 1, 1, 1 would mean that alpha is at the first level, beta is at the first level, and so A, B are jointly distributed, and this joint distribution is known to you, right? Now suppose that you can find the random variable R and two functions f and g, such that for every treatment ij, this distribution inequality holds. This tilde here means is distributed as, it has the same distribution as, right? So you have this random variable R, and also as a second argument the value of the input alpha, and function of course create a new random variable. This R and beta, function g takes them and creates a new random variable. This random variable, now this first and second, they are jointly distributed. Their joint distribution is the same as the one that you have observed, right? So we have an explanation for two things. We have an explanation for selectiveness here, because this function is only at alpha, and this function only of beta, right? And we have the explanation of stochastic relationship, because they are functions of one and the same R, right? And therefore they are not independent, generally speaking.
R must be
Right.
univariate.
Huh?
R is univariate.
Oh no, R is supposed to be completely arbitrary random variable. So you say if you can find a random variable, it can be something, as enormous as something like, the entire universe of possible randomness in the entire universe, whatever, right?
But say R is just bivariate, where the two values are independent.
Yes, yes, independent.
Picks-
Oh yes, yes. Independence is a special case of that, of course. Right, absolutely. So I do not. I only say that it explains the possibility of interdependence, but it allows for independence. Absolutely. Now it's interesting that this is exactly the type of thing, although not in this very notation, that John Bell in 1964 proposed in order to evaluate the possibility of a classical explanation for Bohm's version of entanglement, the one that I've just shown to you. So he exactly proposed these things, and he called this R the set of all possible hidden variables in the universe. And he was thinking about it as thing of enormous complexity. Now, the truth is that when you actually analyze it a bit more rigorously and concisely than John Bell has done it, you will see that this R can always be chosen to be quite simple if your A's and B's are simple. So for example, if this R exists at all, right, at any level of complexity, then I can also choose an R that would be, in this particular case, a discrete random variable with 16 possible values. That's it. As simple as this. So this, if a classical explanation is possible for Bohmian version of EPR with 2 electrons, you only need this simple random variable. And there is a more general result that if A and B are random variables in the narrow sense of the word, so the type of things that we call continuous and discrete or mixed or vectors or something like this, then R can always be chosen as uniformly distributed between 0 and 1, and that's sufficient for everything, right? Of course, if your A's and B's themselves are random sets or random functions or something, then it's a different issue. Then you have to choose R of the same level of complexity, so to say, right? But again, I'm kind of giving you a glimpse of a more general theory behind it. Now, at this moment, we're only having this definition, right? So as I said, this definition allows to say that A and B are interdependent because they are functions of one and the same R. They are selective because this function only has the argument alpha, and this function only argument beta, right? And this distribution equality, of course, in our simplest case, is equivalent to saying that our observed probability Pij, I hope everybody still remembers what it is, P11, P12, P21, or P22, equals the probability that this thing is +1 and this thing is also +1, right? So if you can find these functions and an R, then selective influence is there. And if you cannot, then selective influence is not there. So it is necessary and sufficient condition, if you wish, or a definition. Now, this is another form of giving the definition. And this form of giving the definition has the name joint distribution criterion, which I and Jana Kujala gave to this thing in our 2010 paper. And it turned out to be that in 1981, or 82 actually, Arthur Fine, in a physics paper published in Physical Review Letters, gave exactly the same name to the same criterion. So he called joint distribution criterion. Well, maybe it's not all that surprising because it's a natural name, but it's interesting that we came up not only with the same theorems, but also with the same terminology. Exactly. And of course, you know.
Long explanation.
Huh? Right. So it is a way of putting it in different ways without saying functions and random variables underlying the observed random variables. I simply say suppose that there is a vector h that consists of 4 random variables, and each of these random variables corresponds to one level of one factor. So h11 is the first level, first factor, h12 second level of the first factor, and so on, right? So we have one random variable for each level of each factor, or each value of each factor, and this is my so-called reduced coupling, I call it. And if it exists such that when I choose my A, B, and I choose corresponding H's, they are identically distributed, right? And corresponding H's are obvious. For A, you have to use H with superscript 1. For B, H with superscript 2. And since it is Ij, for A, it will be, for this one, it will be I, and for this one, it will be J, right? So if you can find a quadruple of random variables jointly distributed such that this holds, then you have selective influence. Otherwise, you don't. This is a criterion, necessary and sufficient conditions. This representation and this representation are equivalent, obviously, because it's a criterion. The proof is completely trivial in 2 lines, and by the way, Arthur Fine's proof is long and convoluted. And Pat Supes gave the proof with Zanotti in 1981 of a special case of this, which is even more convoluted. So, you know, it pays off to be rigorous. When you are more rigorous, you can come up with much shorter proofs, right? And the physicists usually are not all that, well, Arthur Fine, is a philosopher rather than physicist, but still. John Bell, of course, is the initiator of this type of proofs, but he did not prove that it is necessary and sufficient condition, right? Okay, so we have these 2 equivalent definitions. This H is called reduced coupling, as I already mentioned. And this is the fact that I've just mentioned to Mark here, that if a representation using some R exists, then R can always be chosen to be very simple. And in this particular case, it is just a random variable with single discrete random variable with 16 possible values, right? So if you can find 16 probabilities that add to 1, you have a joint distribution, right? So this is an example of the situation when this coupling does not exist. So, you know, just in case someone did not know about these quantum things and wondered whether this definition is empty, that always can be satisfied. No, it is not always satisfied. This is an example, so this is a certain distribution with some epsilon, and epsilon is very small value. It is constructed in such a way that the marginals are 1/2 everywhere, right? So it is our situation. And it turns out that if epsilon, now at this particular moment I forgot, but I think if epsilon is negative, this representation exists. As soon as it's positive, it doesn't exist. It may be the other way around. You know, I do not want to exercise my mental capacity now to figure it out, but one of the two. So when you cross 0, the existence of this reduced coupling disappears, right? So it exists for, let's say, negative epsilons, doesn't exist for positive. Okay, this is a theorem that can be considered to be an operational criterion for this joint distribution criterion. So it is another criterion, but this time, unlike JDC, which is completely general criterion, this particular one is confined to my simple situation, which is abbreviated here. Binary, completely crossable inputs with binary outputs with equal outcomes.
I read that on the tape. That's exactly the acronym he used.
No, this one I came up with my greatest achievement is this one. So, this is a set of 4 double inequalities, so 8 inequalities in total. You can begin with 1, 1, and you will have one inequality with 1, 2, another inequality 2, 1, and so on. So, if your piece that we agreed already is the only observable thing from our experiment that we need to care about, if this particular linear combination is between 0 and 1, then this representation exists. So this reduced coupling H exists. if this inequality is violated somewhere, so if one of them is greater than 1 or falls below 0, then it doesn't exist. As simple as this, right? So again, I remind to you that this sometimes it's called CH-SH inequality, but actually it is not correct. Correct would be to say CH, because in so-called CH-SH paper, this inequality has not appeared yet. So it is 1974, first appearance of this inequality, and then Fine, of course, proved that this inequality is also sufficient. The necessity of this was known in 1970-something, 72 or 4, I forgot. Klaus and Horn paper, 74, I think, right? So whatever. So this is the criterion. Now, if you plug in the values for entanglement paradigm, and you choose these values in such a way that, you know, the first orientation is 0, the second orientation is 90 degrees, this orientation is 45 degrees, this is negative 45 degrees, then according to quantum mechanical machine, you will get the value 1 plus square root of 2 over 2, which exceeds 1, right? And that's a violation of the classical determinism. So we need new form of determinism, and it's called quantum now, right? But for quantum time of determinism, there is its own boundary, and here it is. It is not just, you simply violate classical and that's it. You still have to be between these two values. Now this is called Cyril-Sons, or Cyril-Sons. It's a Russian name that can be transcribed in two different ways. Inequality, which was proposed in 1981, together with, before Fine's paper actually was proposed. But the question now is, what does it mean? What is it the condition for this particular inequality? We know that we have already violated, or it is possible to violate the classical determinism. So what for is this condition? Well, it is for the following. For the existence of so-called quantum representation. Quantum representation means that there are Hermitian operators A1, A2, B1, B2 in two-dimensional Hilbert space with eigenvalues +1, -1 each, such that each A commutes with each B. It means, it's just 2 by 2 matrices. Two matrices commute if their product is commutative, right? So each A multiplied by B is the same as B multiplied by A. But the two A's need not commute, and the two B's need not commute. They may, but they need not, right? So for the existence of this representation, with the quantum machine that computes the probabilities in this way, that our Pij's, if we multiply them by 4 and subtract 1, it is the expected value of the product of A and B, and this expected value is given by multiplying some density matrix, which represents the state of the system, by the product of A's and B's, right? And you take the trace of this thing, the sum of diagonal elements, and this expected value, then, this formula should hold, right? So if using this formula, these type of things exist, these Hermitian operators A1, A2, B1, B2 exist, then this inequality should be satisfied. It is not a sufficient condition, it's only necessary. And for sufficient condition, the situation is quite a bit more complex. I will not get into that in my presentation. It makes computations more difficult because strictly speaking, sufficient condition is not known. We have sufficient condition for somewhat a bit more general situation, and that sufficient condition is too complex to deal with in this context. So I just want to confine my attention to this one because it represents kind of a signature of quantum determinism in the same terms with respect to the same linear combinations as we have in Bell-CH fine inequalities. Of course, this is chaos. Like, imagine that we have a universe in which everything is possible, right? So determinism is completely relaxed to the kind of so relaxed that there are no physical laws constraining anything, but there are still laws of arithmetic that would constrain things from happening. These laws of arithmetic dictate that this linear combination should be between 1.5 and negative 1/2, right? So this cannot be violated in principle, right? But this gives you kind of boundaries of the universe of possible determinisms, within which quantum is a special case and classical is even more restricted special case, right? Now what is nice about these inequalities, all three of them, is that they are all linear, right? Which means that geometrically, well, okay, chaos means the existence of functions where, these functions f and g are not selective, in fact, right? So if you allow for any functions f and g that depends on both alpha and beta, this is what chaos is. So essentially, what a physicist would call chaos in the case of entangled particles, in a situation related to psychology experiment, would be simply that both inputs influence both outputs, right? And so there is no mystery there or no kind of, cosmic interpretation for this. But in physics, it is kind of a cosmic interpretation. If we had a universe in which, these boundaries hold, but quantum do not hold, then we would have something like chaos, right? Okay, this is a critical junction now, because that allows me now to switch to violations. And of everything I discussed so far, I worked out quite some time ago, so it's kind of older stuff. Now I'm talking about new stuff. Chaos means actually that when only chaos holds and nothing more restricted holds, then it means that I should find a complete coupling, not reduced coupling as before, but complete coupling where my h's are indexed by both levels of both factors, right? So now I have 8 of them. They are jointly distributed in such a way that when I choose A and B for a particular treatment, then corresponding h's for the same I and j should be chosen and they are identically distributed, right?
64. 64 different values. There's probability.
Yeah, each of them is binary,
Yeah.
right? So you have 2 to the 8s,
Yeah.
and this is indeed 64, right? This is what can always be found. So this coupling always exists, right? And that's the reason for calling the situation chaos, right? You don't have any constraint, right? In fact, in this particular case, what is constructed here, and I call it complete coupling, is what in theory of probability called a coupling, right? It would be a true coupling for what I have observed. I observe 4 pairs, and for these 4 pairs, I put them all together, 4 pairs, and I create 8 random variables. They are jointly distributed. This is a coupling now, right? This theory exists in theory of probability for quite some time, and interestingly enough, people still continue to talk about Kolmogorov's probability as if it were assuming one and the same sample space for everything, right? Not true. It is theory of coupling is within Kolmogorov's theory, right? And it has to acknowledge the existence of stochastically unrelated random variables for which under certain circumstances you can find couplings. So you can put them in system jointly distributed. Okay? So if it exists always, and in the classical determinism we can reduce this complete coupling to our reduced coupling, right? Then the question is, we have this very nice formulation of the, so this delta now stands for this linear combination. We have 4 of these linear combinations. And we have quantifiers here, so it's for all ij, and here also for all ij, omitted. So for this situation, we say it is a necessary and sufficient condition for the existence of functions f, g, and random variable r such that, and we have this, right? For chaos, we have analogous formulation without selectiveness, right? What would be the analogous formulation for quantum? That's what's missing. We have nice classical formulation of the situation in the classical, for the classical determinism. We have it for the chaos. We do not have it for anything else, right? And so this is the task that I and Jana Kujala decided to tackle, to create a language that allows us to formulate all intermediate cases, not just the quantum one, but all imaginary ones, right? All imaginable ones. So let's say this, right? It doesn't have to be this particular inequality, but let's say for this inequality, I say, I conducted psychological experiments and I found out that this delta is always between m and m. Now it may be a special case of the classical determinism. It may be between classical and quantum. It may be above quantum. It may be not a proper subset of any of these things, right? For this m and m. Can I handle it? Is there some way I can describe this type of determinism, right? In the terms that would be analogous to these ones. And here these couplings help us quite a bit. So I have reformulated so in the classical case the coupling is reduced, and in the chaos case the coupling is complete, and this complete reduces to this one. In what way it reduces? Let's look at it in detail. A reduced coupling means that the probability that H with upper index 1 and lower indices 1, 1, 1, 2, the probability that these two will be unequal is 0. So it's one and the same random variable, right? Why is that so? Because one is, superscript 1 means that it is for alpha, right? And this is the value of alpha, first value. And here it is also first value, right? So if the distribution of H doesn't depend on the second index, then it doesn't matter whether it is 1 or 2. It should be one and the same random variable, right? Therefore, the probability that they are not equal to each other is 0, right? Analogously for this one here, right? If it is 2 and 2, then it doesn't matter that the second one is 1 or 2, right? Or here, if it is 1 and 1, the second one now, because it's for beta now, the superscript is 2, right? Then it doesn't matter whether alpha is 1 or 2. So I can obtain reduced coupling from this complete coupling by postulating this set of equalities, that the probability with which the things that differ in the wrong index only, that they are not equal to each other, is 0, right? So if this is true, then I've obtained this reduced coupling because I simply take these two and I denote it by this, right? Or I take these two and denote it by that, and so on, right? Now, this is an idea. What if we replace this? Well, okay. Why is it that we cannot resolve this problem empirically? Because these two are not jointly distributed, right? H with superscript 1 and with index 1, 1, and the other one was index 1, 2, they correspond to these two A's. And these two A's cannot co-occur. They are occurring under different conditions, right? Even though you are changing the wrong index, you are creating a mutually exclusive condition, right? So these probabilities are actually completely unobservable. And the fact that we postulate them equal to 0, from that point of view, is arbitrary. We do not observe them at all. So why should they be 0? Right? Why wouldn't we now replace zeros with some epsilons? If the epsilons are zeros, we get classical determinism. Epsilons at the largest possible value, which would be 1/2 in this case, then we get chaos. Everything else is in between. And these different things, different epsilons can have different values, right? So this is the idea, and this is what determines the program. Now, I believe if 7 minutes was my kind of limit, then I have to wrap up and simply say that what we have here, we have observable vector of probabilities, P1, P, and so on and so forth, right here. And we have this vector of unobservable probabilities, epsilons, that create essentially matrices that look very similar, but they have profoundly different meaning. They are unobservable, and we call them connection probabilities. And the question is to find the combinations of observable probabilities and these connections that satisfy certain principles. Now, what kind of principles? I'm only going to mention it so that I can finish. Principles are as follows. These are technical things that I probably do not have. Actually, I simply do not have time to explain. So, the first problem would be find all pairs of these vectors, observable vectors and connection vectors, for which this coupling exists. So they would be called compatible p and epsilons, right? So some p's and epsilons would be incompatible. They cannot be put into joint distribution, right? So it is the first question. The question is solved by observing that, this set of compatible p's and epsilons, they create an 8-dimensional polytope, and you can describe this polytope very nicely. Now, what you can look then at the following thing. You can look at, for any constraint imposed on your observable probabilities, classical constraint, quantum constraint, some imaginary constraint, or chaos. For any constraint, you can look for the set of epsilons that are compatible with p's under this constraint, right? That now we are looking at 4-dimensional polytopes. And here are the descriptions of these polytopes in some terminology that I haven't explained, so you should. So just some algebraic description of the polytope that creates this set of compatible epsilons, connections, right? The second question that's perhaps even more interesting. Find this is 8-dimensional. So this is the one that I've just described to you. So find epsilons such that if constraints holds, then p and epsilon are compatible. ELFP means compatible. I mean, it means extended linear feasibility polytope, but for our purposes, just compatible p and epsilon, right? Now, the second question is find the set of epsilon such that if they are compatible, then the constraint is forced, right? So it will be under what conditions, under what epsilons you have to have quantum determinism, or under what you have to have classical determinism, or any determinism that you would come up with, right? You can answer this question. It's again a polytope. These are volumes of the polytopes that I do not have time to comment on. They are very interesting to discuss. They are very small volumes, meaning that there is a very small subset of these epsilons that would force your observables to satisfy quantum constraints, right here. Right? And this means that the dimensionality of the things that force classical constraint is below 4. So the 4-dimensional polytope is 0. Right? Now, and finally, I can look at equivalence. I can look at such epsilons that they are compatible with the observable piece if and only if the constraint imposed on this piece holds. Right? Equivalent. And again, you can construct this polytope, you can define these sets, you can compute their volumes. Right? Comparing these volumes is a very interesting thing, but I ran out of time. This is, by the way, what I would call signatures of different types of determinism. This is for chaos. This is 8-dimensional volume for p's and epsilons. This is the 4-dimensional volume of all epsilons compatible with the chaos. This is 4-dimensional set of epsilons that force chaos. Obviously, everything forces chaos, right? Absolutely everything that you would do would force chaos. And these are equivalent. Or this signature is the signature for quantum determinism, right? So it is the volumes of the polytopes. This small volume is the volume of epsilon such that when they are compatible with your observables, then observables have to satisfy quantum constraint, right? this small volume, and so on and so forth. Let me see what I will skip this, and I have some conclusions that kind of set up the program for the future, and I'm not going to discuss it because I do not have time. So this is the end.
If we stick to the program, we have 1 minute for questions, or the boss may decide that we meet later. That we meet later in the afternoon.
Why don't you have about 2 minutes of questions, take 1 or 2 questions and then just.
Okay, two
Because
questions.
once it takes a while.
Sir?
I do an experiment and I discover that the inequalities, the classical bounds are violated, but I'm not so extreme to be chaotic. I'm in the quantum region. To
Right.
what extent can I take that as evidence for sort of some underlying quantum mechanical structure?
Well, to small extent, because the things that we have considered for quantum case, the inequality was only necessary but not sufficient condition. If we dealt with necessary and sufficient condition, and for, let's say, for a quantum experiment, the necessary and sufficient condition for a quantum experiment with 2 entangled electrons will be given by a certain set of equalities, not inequalities, right? With all this cosine squared and whatever. So this would be your constraint, right? That's what we are doing right now as we speak. Yana Kuyala, hopefully, is writing this program that computes these things. For this particular constraint, we can, compute things. So if you have done this experiment that in quantum physics people have done, and found these things, established these laws, then I can characterize it within this general framework. And notice this framework is completely classical, not a single mentioning of quantum, of quantum entities, except in the derivation of these things. So, for example, when Cyrilson derived his inequalities, of course, it should be derived from inside quantum physics, right? Otherwise, how would I derive it? So there we are using this. But my ambition, so to say, my hope is that maybe, we can really use this classical language to characterize not only interesting parts of quantum physics, such as entangled particles, for example, but also, outside that. Because, people sometimes, like in the experiments with combinations of concepts, some of our colleagues are trying to find violations of classical determinism there, or better to say selective influence there. And, and it is not, well, it hasn't been very successful so far, but my point is this: suppose that you don't get violations in behavior. Our behavior is completely classical, but it doesn't mean that we have to, our behavior exhausts the whole range of classical possibilities, right? Maybe we are a special case of classical determinism. It is still interesting to characterize it, right? Not simply say we are classical machines, but say we are special kind of classical machines, right? And for this, you still need this language, because it is lacking. Yes?
Yeah, I think this actually ties in with the last point you were making. Part of the structure of the argument here, and it was a very clean description up to the Bell constraints, but we did the constraints on determinate values and the deterministic evolution of those values. Here, by fixing something that you wanted to fix up front, and that is some kind of locality assumption. We don't want to do violence to the constraints of special relativity, for
Right.
example, and allow apparatus settings on this side of the EPRs
Right.
to determine the outcomes on this side.
Right.
But of course, there are 2 things on the table when we consider Bell-type inequalities. And that is, we have locality constraints that we can play around with, and we have deterministic constraints we can play around with. We know we can recapture classical determinism in the context of a theory like quantum mechanics. And Bell knew that too, right?
Right.
That's how he understood his theorem. Bowling mechanics is great,
Mm-hmm.
but it violates the constraints of special relativity. Can I find a formulation of Bowling mechanics that doesn't violate those constraints and still gives me classical determinism? And his answer was no, right? If you get classical determinism, then you violated the constraints of relativity. But the moral he drew from it was, so Bohm's theory is the best I can do, and he ended up a lifetime proponent of that.
Right.
There we have classical determinism all the way through.
Yes, yes. It is a good comment, and my very brief counter comment, so to say, or additional comment, is that it's exactly why I do not want to touch the issue of what causality or determinism or context are, right? So if you want to say that there is locality, right, and there is sort of therefore measurement of Alice's does not affect the outcomes in Bob's particle because of the relativity theory, it's fine. Then I will simply say it is a different type of determinism that I'm doing, right? If you want to say that it is a violation of selectivity and locality is not there, I will say, well, it is the type of violation of selectivity, right?
So you want to package the locality assumption as the type of determinism.
Exactly, exactly. Because I want to remain neutral. I really do not know what
I see.
physicists will come up with.
Context to map out those.
Right, right.